Okay, welcome back. We'll continue our reviewing. So this is 1.2, 1.3. 1.3. And yeah, we'll review functions and trigonometry. So let's just put functions. And trigonometry. Okay, so let's start with functions. Let me underline it. So functions. So we'll start with, so I'm going to give you a couple equations of functions, and we'll talk about domain and intercepts, maybe graph it, things like that. Yeah, so we'll start with, what do I have here? Example 1. So example 1, and here's the function. So f of x equals 1 over x minus 1. Okay, so this is a rational function, or maybe also called reciprocal function. And yeah, we'll do a couple of things with that function. Well, let's start with evaluating the function. So let's call it A. So evaluate. Somehow my writing today is worse than yesterday. I don't know. For x equals 3. Right, so we simply do f of 3, and we plug in, substitute 3 for x in the function. So we go 1 over 3 minus 1. Right, so that 3 replaced x in the function. So we get half, 1 over 2. Right, so now we have a point, and that point would be 3 comma half, and that point is on the graph. And we just checked it, we just calculated it, and it's on the graph. So yeah, next thing, maybe let's look at, let me add some color here. So first thing we did, we evaluated the function. The second thing we'll do is we'll find domain. So this is B, domain. And yeah, so we need to figure out what are the x's that we can use in that particular function, or what are x's that we cannot use. Maybe that's a better question. All right, so yeah, it's kind of easy to see, right? So the only problem, the only issue that we have with this function is that, let me write it here. So f of x, so that we can see it clearly, is 1 over x minus 1. Right, so on the previous lecture we had a function that had a square root, right? So this one doesn't have a square root, but has a denominator. So we cannot have a 0 in the denominator, right? So maybe let me make it red. Okay, so I cannot put a number that would give me a 0 in the denominator, right? And that number is 1. And if I plug in 1, I get 0 in the denominator, and that's an undefined number. We cannot have it, so we need to exclude that 1 from the domain. So we could do it in a couple different ways, right? We could write it, maybe that would be the simplest way. So x just cannot be 1. Okay, so that's one of the ways. Another way would be interval notation. So I would go all the numbers from negative infinity to all the way to 1, right, are possible. Then I'm excluding that that 1 using parentheses, then I have a connector OR, and then I go 1, again excluding 1, right? So all the numbers are close to 1, of course on the on the right side, right, this time, and then to positive infinity. Okay, so that's another way, and maybe we could also write something like this. So all real numbers except or minus, right? And I'm using those curly brackets to indicate that I only mean 1, right? So let's say, let me give you another example quickly with this particular notation. Okay, so say if I had a function like this. So this is like a side note. So side note. Let's say I have something like this. So f of x equals, I have 1 on the top, and at the bottom I have x squared minus 4. Okay, so in this case, if I wanted to figure out what domain is, right, it would be the same thing, right? I need to exclude the numbers that give me 0 in the denominator, and there are 2 of them. Right, so I could do it like this, 2, negative 2. I could do it interval notation, which is kind of, right, lengthy, but maybe the best way would be to write it like this. So all real numbers except, and now again, right, I'm using those curly brackets, and now I'm putting those 2 numbers, negative 2 and positive 2. And then those curly brackets means that this is not an interval, these are just elements, right, of the set that we want to exclude. Anyway, let's go back to our initial example. So that was what? F of x equals 1 over x minus 1. Okay, so let me write it here, maybe here. So I have f of x 1 over x minus 1. So if I want to, so this is right, the graph. Well, let me just write, because that's what we were doing next, right? So graph of that function. All right, so we have basically a reciprocal function and parent function. The easiest function, the most basic function of that group of functions would be 1 over x. All right, so let me just write it. Parent function would be f of x equals 1 over x. All right, so reciprocal or rational function. So let's graph it. All right, so we could graph it the way we did it last time. We did it using, let me move it up. We did it using what? We were plotting points, right? Making a table, plotting points. So this time, we're just going to sketch it. Right? So I just know how the function looks like. Let me make it maybe blue. Right? So it's a hyperbola and it looks something like this. Okay. And those arrows. So we have 2 branches of that function. And we have a vertical asymptote, right? So that vertical, well, we have both, right? Horizontal and vertical. But in our case, that vertical asymptote is, I don't know, in a sense more important. It's because when I graph that actual function, right, this one, f of x, right, so this one, right, so I'm actually graphing this function, right, this is my original function. So what's happening is that it's basically the same shape, right, of that reciprocal parent function, 1 over x, but it's moved, the graph is moved to the right. So what I'll do, I'll take that vertical asymptote and I'll move it to the right by 1 unit. And let me make that 1 unit actually over here, right? So this would be 1, 2, 3, and then -1, -2. So this is 1, 2, and 3. Okay, so now I'm moving that asymptote. Let me maybe make it a little bit better. Okay, so this is the asymptote. I don't know if it's better, but I hope. Well, it's not, it's not shifted, right, to the right. Anyway, so now this one is shifted, right? That was kind of the point of erasing it. So now I just take my graph and I shift the whole graph to the right. So let's make it maybe, I don't know, yeah. Okay, so same shape, and I'm just shifted it to the right, right? And so this is that upper branch, and now that lower branch will be here. All right, it's not perfect, but it is what it is. Okay, so the equation of the yellow one is 1 over x minus, we make those ones like this. And then the equation of the blue one, right, it's y equals, I touch the screen with my hand, and then, right, that's what happens. So this one was 1 over x. Right, so the yellow one is shifted by 1, and that shift, the number that's responsible for that shift to the right is this one. Right, so shift to the right by 1 unit. Okay, so what else do we have? Yeah, we had a point, right? Let's put that point on the graph. So that point was 3.5, right? So that would be right there. And I don't have space, but basically it's 3.5. Okay, so that's the point on the graph. All right, so that was a rational function, a reciprocal function. Let's look at absolute value function. Right? It's also quite important. Okay. So this is example 2. And this is, absolute value function. I should have written, right, what that other function is. It was a rational function. But anyway, too late now. So absolute value function. And it, you guys know what that is, right? So it's f of x and then absolute value of x. All right, so that's the equation. Here's the definition. It's a fun definition. All right, f of x. All right, so we have that absolute value of x, and it's defined like this. So it's defined actually using the piecewise function. So that is defined that absolute value of x is x, right? If it's simply x, if x is bigger or equal than 0. And then it's negative x if x is less than 0. Okay, so let's look at a number, make a couple numbers, right, and just kind of figure out what's going on. So let's say, so if x, how would we like kind of understand intuitively this definition? So if x equals 3, okay, so I would use that absolute value. I would put 3 here. And what is 3? 3 is a positive number, so it belongs, and it's part of this, the red function. Right? So it says if x is positive, then the absolute value of that is just that, so 3. Okay, so now if x is negative 3, right, then it's a little different. or it's exactly the same. Well, anyway, so I have an absolute value of -3. So now let's look at the definition, right? So now I'm in the blue part of that piecewise function. Let me make that more prominent here. Okay, so so it's if x is less than 0, so that's our case, we need to take the x and just copy it there. Right, so -3 is my x, but then I have, right, in front of it, I also have that negative, and that comes from the definition, right? So this blue negative is not part of the, right, of the actual number. It's part of the definition. So now the result is 3. Okay, so that's how that definition works. Let's look at the graph, right? So I don't know if you guys remember how to graph those, the absolute value function or functions, but it goes something like this. Right, we have coordinate system xy, and then yeah, so we have x for x is bigger or equal than 0. Let me make it. Oh, this was supposed to be red. Okay, so so let me just kind of graph y equals x, right? So this would be y equals x, right? So this is y equals x. See, I got lost again. Okay, right, y equals x, but then it says, right, for x is bigger or equal than 0, right? So those x's here on the left of the y-axis, right? I don't need this part, right? So I'm going to erase it. I need this part, and also 0, right? Is part of that function. Now I have the part of that branch. Okay, now I have the blue function, right? And again, so the blue one will be y equals -x, so I have negative slope. And here again, I don't need that right branch, right? Because I only need x's that are less than 0. So yeah, I need to erase this and make this solid. All right, yeah, so that's the absolute value, but you guys already knew that, right? Maybe you not necessarily knew where it's coming from, but anyway, so this branch would be that -x, right? So -x, and again, okay. All right, so that's absolute value. Well, actually, let's. There is one more thing. Let's look at the domain. That was not supposed to be blue. That was supposed to be white. So domain. And then, as I was explaining last time, for domain we kind of project the graph on the x-axis and just kind of look at what part of the x-axis is covered. So the whole x-axis is covered, right? So any x works in that function. As for range, actually that's different, right? Because a range is not the entire y-axis, right? If I projected the whole graph, so right, I would be doing kind of putting all the points against. Again, I'm touching the screen all the time. Sorry about that. All right, so I'm putting the points against the y-axis. Okay, so you see that, right, this part of the y-axis would be covered, right, with our graph. So that range would be from 0, right, including 0 to positive infinity. Okay, so next thing I'd like to review is one-to-one functions, and that's going to be important when we discuss inverse functions. All right, so one-to-one functions. Yeah, let's make it just regular white. So one-to-one functions. So the idea is pretty simple. Basically, 1x, right, goes to only 1y, and yeah, that'd be kind of the intuitive way to understand one-to-one functions. But let me give you a definition. So definition. So a function is one-to-one. So one-to-one. From a set x to the set y. Alright, so x, y. If each y value in the range corresponds to one value of x in domain. Or in the domain. Yeah, so so there's this y. Let me give you an example of something that's not a one-to-one function. Okay, so here you go. So not one-to-one, or let me maybe. Right, so we have some set of x's, 1, 2, 3, and then set of y's, 4, 5, and 6. And let's say that this 1 goes to 4, and 2 also goes to 4, and then 3 goes to 5. All right, so you see that, so this is these are x's, and these are y's. All right, so according to definition, one element of y, right, would have to correspond to only one element of x, and this is not the case, right? So you see that 4 corresponds to 1 and 2, right? So this one is not one-to-one. Not one-to-one. Another example of something that's not one-to-one would be a parabola, right? So let's sketch a parabola. We can just do regular parabola, just y equals x squared. So this one is y equals x squared. And for example, let's look at what is that? Let's say this is -2, right? This is +2. And you see that both of them correspond to the same y. Alright, so this is 4. So in a sense, right, so 4 would be element of range, and then those two numbers would be elements of domain, right? So there would be -2 would be here, 2. And then in this set, right, we could have other numbers here, right? 1, 4, and what would happen? Those two numbers will go to 4. Right, so not 1 to 1 again. So not 1 to 1. All right, so how about a function that actually is 1 to 1? We can fit it in here. So let me give you a graph. Okay, so for example, a cubic function, right? So y equals x cubed. So this is y equals x cubed. And this one is 1 to 1, right? Because, yeah, you cannot find numbers that, two numbers or more numbers that would correspond to the same, or two x's that would correspond to the same y. And also there is something called the horizontal line test. I'm not going to give you a definition because it's a pretty simple concept, horizontal line test. It goes something like this, right? So if you can find a line, horizontal line that crosses the graph in more than one spot, then the function is not 1 to 1, right? So in here, right, there's no way we can find a horizontal line that would cross our green graph in more than one spot. But over here, right, if that in that quadratic function, right, basically almost every line, right, would cross our graph in two spots, right? So you see it's crossing here and it's crossing here. So not 1 to 1. This one is 1 to 1. So this one is 1 to 1. And yeah, that's the idea of one-to-one functions. So next idea was related to symmetry. It's basically the same concept, the same idea. So this is called, we don't need that. I don't know, we could call it symmetry. So something we talked about yesterday. And I already kind of told you that, right? So we have two types of symmetry, or we have three types, but one of those types, right, the symmetry with respect to x-axis doesn't really apply to, in calculus, because that would give us something that's not a function. But there are two other types of symmetry. So we have even functions, and odd functions. So those, the even functions, I don't know if you remember, basically that was symmetry with respect to y-axis. So the condition for that was like this: f of x is the same as f of negative x. And odd functions were symmetrical with respect to the origin. And the condition was something like this. So f of x is the same as negative f of negative x. Or, right, that this negative can be on the other side. So negative f of x is the same as, is equivalent to f of negative x. Okay, so even and odd functions. Okay, so that's that concept. Yeah, so let me summarize those. Let me give you maybe a list of those basic functions that we will be using quite a bit. We'll be using other functions as well. Basic functions. So it'd be good if you guys Maybe I'll functions. It's supposed to be I. Okay, function. All right. So the first one is f of x equals x. I don't think I need to graph this, right? So it's just a straight line. Right, 45 degrees. F of x equals x. So that's the first one. The second one is x squared. That's a simple parabola. I'm just sketching it quickly. Okay, next one is I have cubic function, so f of x equals x cubed. Okay, so cubic function. What else we have? And then I have, next one is, let me write it here. So f of x square root, so square root of x. You know, that doesn't mean we won't be using other functions. But yeah, these are probably the most commonly used. All right, so graph of square root function looks like this, something like that. 0 belongs to that function. And the last one, I have that absolute value. If we can squeeze it in here, maybe. So the last one is absolute value, so f of x is absolute value of x. And you just saw the graph, right? So it's something like this. That's absolute value. Okay, so these are the basic 5 functions that we'll be using quite often. And yeah, next thing I would like to review is transformations. So that means basically shifting graphs up and down, left, right. And also, you know, there's those compressions and stretches, right? So let me just quickly review. The most important part is those shifts. So let's review that, and then maybe if we come across a problem that we'll need to understand those stretching and compressing the graphs, then I'll review that. So transformations. Yeah, so what this is about is, let's take let's do an example. So example 1. So what we need to do is graph using transformations. Okay, and here's the function f of x equals square root. I wonder if I made it a little bigger. It'd be easier to write. I don't know, we'll see. So square root of x minus 3 and then plus 5. Okay, so we have a couple things going on here. And we need to graph those couple things. Yeah, so first thing, when we were graphing those, when we were using transformations, when we were graphing functions using transformations, we always start with that parent function, right? So the most basic function of that particular family of functions, right? So square root of f of x would be something like this. And I'll make it dashed, right? Just kind of showing that that's not really my final graph. And then what we need to do next, right, is that minus 3, right? Because I follow the order of operations, or I think about it in a different way. I think about it, what is done first to x, right? So first thing that's done to x is 3, right? Subtracted from x, right? That's the first thing. So what that means is that I need to move the graph by 3 units to the right. Okay, so 3 will be here, 4, this is 2. Yeah, so I'll take the graph and I'll move it 3 units to the right. And then the next thing that's happened to x is plus 5. Alright, so I take the graph, and when a number is outside of this function, that number is responsible for moving it up or down, right? So I'm adding numbers, so I'll be moving it up, right? So 1, 2, 3, 4, 5. So it needs to go over here, right? So my graph will be the same shape, right? The shape hasn't changed, and here's the graph, right? And that point, right, obviously belongs to the graph. Yeah, so we could, of course, do many other problems, and it gets quite complicated, but yeah, there's no time really for that. Let me just write that coordinate, so 3, 5. Okay, so that was transformations. That's the most important part of it, right, of those transformations. And yeah, so we're done with 1.2. So this is, now it's going to be 1.3.